Good morning. Welcome to the Design of RC Structural Elements course to the next session. In the previous session, we were discussing or we were doing some certain problems in singly reinforced beam. In continuation with today, we will do some more problems of singly reinforced of type 1. Okay, in type 1, today I am going to solve one more problem. Let us see. Okay, what is the problem? A rectangular beam of section 250 mm wide and 500 mm deep up to the center of tension steel. 250 mm wide and 500 mm deep up to the center of tension steel consists of 4 numbers of 22 mm dia bars, full stop. If M20 grade concrete and Fe415 steel is used, find what concentrated load it can carry at midspan. Find what concentrated load it can carry at midspan if the beam has an effective span of 6 meter. Okay, so this is the thing it required. So let us first write down the data. The data are B is equal to 250 millimeter. Okay, then carefully observe 500 mm deep is up to the center of tension steel. That means if this is the cross section, of a beam, of dimension 250 millimeter, which is reinforced with 4 numbers of 22 mm dia. 4 numbers of 22 mm dia. As we know, okay, always the reinforcement will be provided on the tension side. Okay, and this will be the neutral axis. Okay, so now what is the dimension they have been given is effective depth directly. Instead of mentioning effective depth, they have given in such a way that 500 mm deep up to the center of tension steel, that is from extreme compression fiber to the center of or central axis of tension steel, D is equal to 500 millimeter. So therefore effective depth D is equal to 500 millimeter. Then AST 4 numbers of 22 mm dia. So same thing, 4 into pi by 4 into 22 square, which work outs to be 1520.53 millimeter square. Next, grade of concrete 20 Newton per millimeter square. Grade of steel 415 Newton per millimeter square. Okay, and one more thing they have been given, effective span, that is LE is equal to 6 meter. So these are all the things they have been given in the problem. Okay, so when you want to work out or when you want to get the concentrated load, okay, that means first I need to decide the section. Same thing, whether it is under reinforced, over reinforced section, first we need to decide. Okay, so then we are going to come across with these things. Okay, so next, first let us decide the section. The same thing, step number 1, depth of neutral axis. Depth of neutral axis, same thing as per annexure G 1.1a, page 96 of IS 456-2000. The formula will be XU by D equal to 0.87 Fy into AST divided by 0.36 FCK into B into D. Okay, therefore XU by D equal to 0.87 into Fy is 415 into AST 1520.53 millimeter square divided by 0.36 into FCK 20 into 250 into effective depth 500 millimeter. So this workouts to be XU by D equal to 0.60. 0.60. Next, same thing, maximum or limiting depth of neutral axis, maximum or limiting depth of neutral axis, that is XU max by D or XU lim by D equal to, okay, so same thing, okay, as I stated, okay, the XU max by D or limiting depth of neutral axis will vary, okay, based upon the type of or a grade of steel we are going to use, okay, as mentioned in page number 70 of IS 456 2000. Okay, for this, for Fe 415 steel, okay, XU max by D equal to 0.48 as per page 70 of IS 456 2000. Okay, next, step number 3, that is deciding the section. Since XU by D greater than XU max by D, this implies a section is over reinforced. A section is over reinforced. Okay, so for over reinforced, how to calculate the limiting moment of resistance or ultimate moment of resistance? Because in the last class itself I have been stated, okay, in the code book they have been clearly specified. They have been clearly specified, okay, in the annexure G, over reinforced means two cases will come, R2 formula, G 1.1b, page number 96, holds good for under reinforced, G 1.1c holds good for over reinforced. So now, since it is over reinforced case, you can use that particular formula, that is annexure G 1.1c formula as I have written, okay, that is page number 96, mu lim equal to, you can use this formula, that is mu lim equal to 0.36 XU max by D, 0.36 XU max by D, okay, multiply by 1 minus 0.42 XU max by D into BD square FCK into BD square FCK. This is the formula you can use, or you can go ahead with a few more formula. Mu lim equal to 0.138 FCK BD square. So this formula holds good for Fe 415 steel. In the same way, if it is for some other type of steel, for example, if it is 250, it will be 0.148 FCK BD square. If it is for Fe 250 steel, if it is 500, 0.133 FCK BD square for Fe 500 steel. Okay, so these are all the formula. So now we can use this formula or you can use this formula. Okay, so I will go to substitute with this simple formula, 0.138 into 0.138 into FCK is 20, B is 250, okay, into effective depth 500 square. Okay, so this MU limb workouts to be 172.50 kilonewton meter. So this will be also considered as MU because it is a over reinforced section. Okay, over reinforced section, we are going to limit the moment of resistance that we are going to consider ultimate moment of resistance. It is one and the same. Okay, because it is a over reinforced section. Is it clear? So now you come across with this ultimate moment of resistance. Okay, now how to calculate the concentrated load, because in the given problem they have been clearly asked what is the concentrated load that it can carry at the midspan. Okay, so let us write down the heading concentrated load. How to calculate that? Concentrated load calculation. Okay, so now it is a simply supported beam. Okay, it will be subjected to the central concentrated load P. Central concentrated load P. Okay, and one more thing, a very important thing here, as I keep on specifying, the UDL will also be acting on the simply supported beam as dead load. As I specified in the last class, always the dead load will be treated as a UDL. The self weight will be acting as UDL on the beam. Okay, so UDL is dead load and this will be the concentrated load P. But in the problem, nowhere they have been mentioned like live load or superimposed load, and second treated as 0. Okay, the superimposed load will be 0. So if I am going to write down the formula for this unfactored moment formula, that is M is equal to, just you are going to write in strength of materials or analysis class. Okay, I am going to write down a same formula. So a formula for a simply supported beam subjected to a intensity of WDL, then the formula will be W into effective span square by 8, that is WL square by 8. It is a UDL, hence the formula will be WL square by 8 plus, okay, a concentrated load it can carry. Simply supported beam subjected to central concentrated load will be PL by 4. So this is the formula. So now we need to calculate this particular P. Okay. Now let us calculate the terminologies one by one. Okay. So we know that, okay, how to calculate the M. Okay. Since MU is calculated, okay, how to calculate the M? Okay, we know that M is equal to, okay, M is equal to MU divided by 1.5. That means ultimate moment of resistance divided by the factor of safety, partial safety factor. So therefore, that is 172.50 divided by 1.5. So this workouts to be 115 kilonewton meter. 115 kilonewton meter. Then what about WDL? How to calculate WDL? As I have specified, it is the cross-sectional parameters of a beam multiplied by the density. The cross-sectional parameters are B into, okay, B into that overall depth into, okay, the density of concrete. Okay. So now we already know what is the value of B. that is 250. Now we don't know what is overall depth. Okay, because in the problem they have given effective depth, not a overall depth. So how to calculate the overall depth? Okay, 4 numbers are given. Okay, this is the effective depth D. Okay, and this will be your width 250. Okay, so how to calculate this distance? Okay, so this effective cover is required. If you know the effective cover, then we can calculate the overall depth. How to calculate the effective cover? How to calculate the effective cover? Okay, we can calculate the effective cover by clear cover plus diameter of a bar by 2, the same formula. Okay, effective cover is equal to clear cover plus diameter of a bar by 2, because effective cover is also not given, only diameter of a bar is given. Hence we need to calculate the effective cover by using this formula. Okay, let us assume the clear cover as 20 mm plus the diameter of a bar is 22, okay, by 2, that is 20 plus 11, okay, it works out to be effective cover 11 mm. Therefore, it will be overall depth D is equal to 500 plus 31, it works out to be 531 millimeter. Okay, so please be very careful while substituting or while calculating the dead load. It is overall depth, not effective depth. Please keep in this mind. Okay, so 531 into the density of RCC 25. So this works out to be, okay, the value is 3.32 kilonewton per meter. 3.32 kilonewton per meter. Okay, next let us substitute everything in the above formula. Okay, so that is M is equal to, for this formula, that is 115 equal to, okay, 3.32, that is WDL, into effective span is 6 square divided by 8 plus P into effective span is 6 divided by 4. Now calculate the value of P. Okay, so this P works out to be 66.34 kilonewton. 66.34 kilonewton. So like this, you may get the problem in singly reinforced of type 1. Okay, I hope the problem is clarified. Okay, they have asked the concentrated load that it can carry at a midspan. Okay, and one more thing, a very important thing, in the problem nowhere they have been mentioned it as a simply supported or not, beam or not. So hence we are going to consider it as a simply supported beam, subjected to the concentrated load. And as I have stated, the dead load will always be acting as a UDL. The self weight will be always acting as a UDL. Okay, is it clear? Okay. So this completes type 1 problems in the singly reinforced. Now let us get into the type 2 problems in the singly reinforced. Okay. Okay. Now let us get into the type 2 problems in the same singly reinforced beam. Type 2 problems. Okay. So in the type 2 problem, just like in type 1, we are going to know what are all the data they have been given and what you need to find in this particular problem. Okay. So let us write down first. Okay, the given in the problem or the data are The first thing, they will give factored moment or ultimate moment. Factored moment or ultimate moment will be given. Okay. Second thing, total load. They are going to give a total load, that is W, and this is mu. Number 3, span and of a beam. Span of a beam. Okay, that is effective span. Next, size of a beam or dimensional parameters of a beam, that is B into overall depth, or sometimes they may give effective depth. Next, grade of steel and concrete. Grade of steel and concrete. Okay, grade of steel and concrete. Next, to find or required, you need to calculate here is area of steel, that is AST. Okay. So please note here, they will be given factored moment or ultimate moment, total load, span, size, and then grade of steel and concrete. You need to calculate area of steel. Is it clear? Okay. So please observe here, very important thing. In the type 1, they used to give span, size, grade and area. We used to calculate what is factored moment. Okay, in this case ulta. Factored moment will be given, span is given, size of the beam will be given, grade of steel will be given. What is the area of steel required is asking. That is what a type 2. Okay, is it clear? Okay, now let us work out the problems so that you will come across how exactly we are going to calculate or come across with the area of a steel required for a beam. Is it clear? Okay. Let us go ahead with the formula problems. So the problems are, let us work out some problem. Determine the area of reinforcement required. Determine the area of reinforcement required. Determine the area of reinforcement required for a singly reinforced beam. For a singly reinforced beam. For a singly reinforced beam having a cross section 300 by 700 millimeter, 300 millimeter by 710 millimeter to support factored moment, to support factored moment of 185 kilonewton meter. Full stop. Adopt M20 grade concrete and Fe415 steel and Fe415 steel. So like this they have been given in the problem. Okay. You need to find out what is the area of reinforcement required. Okay. Write down in the same way like type 1. The data required are, first, B is equal to 300 millimeter. Is it clear? Okay. Next, since they have been given size of a beam, that means it is capital D is equal to 710 mm, because nowhere in the problem they have been mentioned as effective depth or the depth up to the center of tension steel. Since nowhere they have been mentioned anything, I am going to consider it as overall depth of a beam equal to 710 millimeter. Okay. Next, supporting a factored moment of 185 kilonewton meter. Factored moment or ultimate moment of rest, that is 185 kilonewton meter. Next, FCK 20 Newton per millimeter square, and then Fy 415 Newton per millimeter square. Next, what you need to find? To find is the area of steel. This is the missing data here. Okay. So now you can write down the diagram. Okay. This is 300 millimeter, and then overall depth 700 millimeter. This will be your neutral axis. This will be your neutral axis. Okay. Next, once again, okay, we require effective depth. Okay. How to find out effective depth? How to find out? Okay. So one more thing I can teach you. Okay, is page number 47, table 16. Okay, page number 47, table 16. They have been given. Okay, what is the cover you need to, okay, consider? What is the cover you need to consider? Okay, in particular to calculate. Okay, so referring to there you can clearly see nominal cover to meet durability requirement class 26.4.2. Okay, exposure condition. This cover may be decided as I stated in the last class based upon the cover. Okay, that is based upon the exposure condition. Okay, whether it is mild exposure condition, whether it is moderate exposure condition. So based upon the exposure condition, we are going to decide the cover. So now directly I am going to, okay, consider effective D is equal to overall depth minus effective cover. Overall depth minus effective cover. Please note down, in the table 16, they are not being given as effective cover. Nominal cover, minimum cover need to be considered. Okay, so now, okay, the minimum, okay, they have been mentioned. Let us consider for a mild exposure condition. Okay, a minimum cover or a nominal cover we need to consider is mild exposure condition is 20 mm. Let us consider 35 mm. Okay, so sorry, this is 710. So 710 minus 35. 710 minus 35. So this workouts to be 675 millimeter. So please note down. So this particular data assumed as per table 16, page 47 of IS 456 2000 based upon the mild exposure condition. Is it clear? Because we require effective depth here. The effective depth is not given. Okay, in the type 1, AST will be given. We used to assume a clear cover. Okay, and then the plus diameter of the bar by 2, you used to get the effective cover. But here, effective cover is also not given. Clear cover is also not known. Diameter of the bar is also not known. So then how to calculate? Under these circumstances, go to the code. Okay, a code has clearly specified. Table 16, page 47. Clearly specified what is the minimum cover you need to consider based upon the exposure condition. So I have considered the mild exposure condition. For that, a minimum cover you need to consider is 20 mm. I have been considered 35 mm. Is it clear? Okay. Next, let us consider. So now we need to once again decide in order to calculate the AST. In order to calculate the AST, we need to decide once again the section whether it is over reinforced or under reinforced section. Okay, so how to decide under reinforced or over reinforced section? In the type 1, we used to decide the section based upon, okay, the depth of neutral axis, that is xu by d and xu max by d. So there you people come across AST value, that is in annexure G 1.1. If you, okay, calculate the depth of neutral axis, that is xu by d is equal to 0.87 Fy into AST divided by 0.36 FCK into B into D. Okay, if you are going to use this formula to arrive at the deciding the section, same as type 1, it does not holds good, because here the left one, that is xu by d is also unknown, or xu is also unknown, and right hand side AST is also unknown. You cannot arrive with over reinforced or under reinforced with using a depth of neutral axis. Then how to decide the section? Okay, so this you people have come across in the balanced under reinforced over reinforced section. Okay, that is xu is the one factor, and one more factor to decide. One more factor to decide the section over reinforced or under reinforced is, okay, mu and mu lim. If mu is lesser than mu lim, then the section is called as under reinforced. If mu is greater than mu lim, then the section is called as over reinforced. But in the type 1, we were deciding based upon xu and xu max. But here xu and xu max cannot be found or cannot be found, because AST is unknown. Hence, we are going to use an alternate way to decide the section. Okay, now let us calculate the mu lim or limiting moment. Because already we know what is mu value. Please note this point. Already we know the ultimate moment of resistance of a section, but we don't know what is the limiting moment. Okay, hence limiting moment of resistance, that is mu lim. Okay, mu lim. So now one more circumstances will come. Sir, how to use this formula? As I have stated in the type 1, we were using mu lim, okay, because it was over reinforced section, that is class G 1.1c. Okay, but now we don't know what is the section. Next, what is the formula we are going to use? Okay, in this particular circumstances, I am going to assume, okay, the section as balanced. Okay, the section as balanced. Assuming the section as balanced, okay, then a formula we are going to use, okay, as stated in annexure G 1.1c page 96, for a balanced section or for a over reinforced section, the same formula I can use it. Okay, okay, that is mu lim is equal to 0.138 FCK BD square. Okay, or else, okay, you can go ahead with the page number 96 formula, that is mu lim is equal to 0.36 xu max by d into 1 minus 0.42 xu max by d into BD square FCK. You can use either of the formula, and this formula holds good for Fe415 steel. Fe415 steel. Okay, substitute this. So 0.138 into FCK is 20 into B value is 300 into effective depth 675 square. 675 square. Okay, this workouts to be 377.25 kilonewton meter. 377.25 kilonewton meter. You will get the answer in 377.25 into 10 to the power of 6 Newton millimeter, or I can say 377.25 kilonewton meter. Okay, so now mu is known, mu lim is known. Okay, next comparing mu and mu lim, comparing mu and mu lim. Okay, so now I can say, okay, mu is lesser than mu lim. Mu is lesser than mu lim, hence the section is under reinforced. Okay, I am going to say the section is under reinforced. Since mu is lesser than mu lim, the section will be treated as under reinforced section. Now, how to calculate the area of steel? If you know the under reinforced section, step number 2, that is area of steel. Which is the formula you are going to use to calculate AST for under reinforced section? Once again, as per Annex G 1.1b, okay, page 96 of IS 456 2000, the formula is mu equal to 0.87 into Fy into AST into 1 minus AST Fy divided by BD FCK. Okay, so this is the formula you are going to use. 0.875 Fy into AST into D, 1 minus AST Fy by BD FCK. This is the formula you are going to use, okay, to calculate area of steel. Now substitute. See, please note down, Fy is in Newton per millimeter square, D is in millimeter, Fy is in Newton per millimeter square. Okay, hence substitute the mu value in Newton millimeter only. That is, they have been given 185 kilonewton meter, convert it into Newton millimeter. That is 185 into 10 to the power of 6. These are all the things you need to be very careful. Because, okay, you require the depth in millimeter and Fy is in Newton per millimeter square. Okay, AST you required in millimeter square, depth is in millimeter, B is in millimeter. If you are going to substitute mu in kilonewton meter, the answer will be varied. So you need to be very careful on these elementary things. Okay, so 185 10 to the power of 6 equal to 0.87 into 415, that is Fy, into AST is unknown, into D, effective depth is 675, into 1 minus AST into 415 divided by the width is 300 into 675 into 20. Okay, so if you are going to do this, you will get a quadratic equation, that is 24.97 AST square, 24.97 AST square minus 24378.5 AST, 24370.75 AST plus 185 into 10 to the power of 6 equal to 0. So AX square, okay, so this is what the equation you are going to get. So solve this quadratic equation. So in calculator or in the method of manual method, okay, if you are going to do, so you are going to come across with 829.62 millimeter square. So this is the area of steel you are going to get, okay, in the problem. So any doubts? Any doubts in this? So like this, you are going to work out the problem in type 2. So the given problem aim is to find out AST. So like this we are going to work out the problem. So hope you have understood how exactly we need to solve. Okay, so here the very important thing you need to remember is You cannot use XU max by D formula because AST is unknown here. That condition has been failed. The second condition you are going to use is mu and mu lim. So now, if you are going to use this mu lim formula, okay, then you are going to ask, sir, if it is mu lim formula you are using means I need to consider it as a over-reinforced section. No. Okay, we are going to assume a section as balanced. Assuming the section as balanced as per Annexure G 1.1 C, page 96 of IS 456-2000, calculate the mu lim value because mu is already known. We want mu lim value. So mu lim value is given in Annex G 1.1 C by considering the section as balanced. Okay, so calculate the mu lim value. After calculating the mu lim value with the given mu value, compare it. Okay, comparing mu and mu lim, since mu is lesser than mu lim, it is under reinforced. If mu is greater than mu lim, then it is called over reinforced section. Is it clear? Okay, then calculate the AST value by using Annex G 1.1b. Okay, Annex G 1.1b. So using this condition, calculate the AST. Is it clear? So this, like this, we need to solve a type 2. Okay, let us work out one more problem. One more problem. The next is calculate the minimum effective depth. Calculate the minimum effective depth. Calculate the minimum effective depth required and the area of reinforcement required and the area of reinforcement required and the area of reinforcement required for a rectangular beam having a width of 300 millimeter, having a width of 300 millimeter to resist a moment of 150 kilonewton meter. To resist a moment of 150 kilonewton meter. Full stop. Use M20 concrete and Fe415 steel. Okay, so this is the problem they have been given. Please note down. Here, apart from area of reinforcement required, they have also been asked what is the minimum effective depth or calculate the minimum effective depth. And they have been given only the width of a beam. No overall depth is given, no effective depth is given. In the last problem, they have given the overall depth. But in this particular problem, they are not being given overall depth also. Okay, and they have been given mu value, FCK and Fy. Under this condition, how to calculate the AST? Okay, so first write down the data. The data are B is equal to 300 millimeter, mu is equal to 150 kilonewton meter or 150 into 10 to the power of 6 Newton millimeter. Then FCK 20 Newton per millimeter square, Fy is 415 Newton per millimeter square. Okay, next to find, what are all the things I need to find? To find, okay, is the minimum effective depth and then AST. So these two things I need to find out. So how to go ahead with this problem? Okay, so once again let us go ahead. The same thing here also. To calculate the AST, first I need to decide the section. Okay, in order to okay, calculate the AST, first I need to decide the section. Okay, for that, how to proceed with the problem. In the last problem, okay, all the data were given, that is, okay, effective depth, everything we used to calculate. Now, effective depth is also not given. How to calculate this? First, let us calculate the minimum effective depth. How to calculate the minimum effective depth? Okay, so we need to assume here. Once again, let us assume the section as balanced section. Let us assume the section as balanced section. Therefore, mu lim, once again the same formula, equal to 0.138 FCK into BD square. Is it clear? Okay. So that is this formula holds good once again for a Fe415 steel. Is it clear? Okay. So now how to proceed with this? Okay. So let us consider this mu lim which is equal to mu because it is a balanced section. Therefore, mu is equal to mu lim. Because of mu is equal to mu lim, I am going to rearrange the formula as mu is equal to 0.138 FCK BD square. Okay. So now, okay, what is that mu value? Okay. Or how to calculate this? Therefore, D is equal to mu divided by 0.138 FCK into B within the square bracket. So now, what is the value of mu? Let us substitute everything. So, they have not been given. Okay, sorry. Okay, one clarification here. To resist a moment of, they have been given. Okay, to resist a moment of means it is an unfactored moment. Nowhere they have been considered the factor of safety. Hence, it is a unfactored moment. How to calculate the factored moment? That is, mu is equal to, okay, 150 into 1.5. 150 into 1.5. So this workouts to be 225 kilonewton meter or 225 into 10 to the power of 6 Newton millimeter. So please note that. This is a very important thing. In the problem, nowhere they have been mentioned as factored. Hence, I am going to consider it as an unfactored moment. That means unfactored means without considering the factor of safety. Okay. So now let us calculate the mu value, that is ultimate moment of resistance value, by considering the factor of safety. Okay. So therefore substitute this. Once again same thing, please be cautious. Depth is required in millimeter and substitute mu in Newton millimeter. So 225 into 10 to the power of 6 Newton millimeter divided by 0.138 into FCK is 20 Newton per millimeter square into width is 300 millimeter. Like this, you need to cross check, okay, whether all the substituted units are proper or not. Then only you will get a correct answer. Okay. So this workouts to be, the depth workouts to be, okay, 521.28. 521.28, but practically we cannot provide 521. I cannot say, okay, a mason to provide, an engineer to say construct a depth of 521.28. It is practically impossible. Okay, hence Okay, I'm going to round off this to 525 or 530 millimeter. 530 millimeter. This is the things you need to follow in the design. This is the things you need to follow in the design. Okay. So now depth is came to know. Now how to calculate the AST? The same thing. Okay. The same thing. Okay. Let us use the formula, under reinforced formula, that is mu is equal to 0.87 Fy into AST into D 1 minus AST into Fy divided by BDFCK. So this is the formula you are going to use. Okay, you already know what is mu. 225 into 10 to the power of 6 equal to 0.87 into 415 into AST into effective depth is 530 into 1 minus AST into 415 divided by 300 into 530 into 20. So by substituting everything, you are going to come across with a quadratic equation. So if you are going to solve the quadratic equation, you are going to come across AST is equal to 1450.36 millimeter square. Okay, so carefully you need to solve, okay, and get the value. So like this, we are going to work out the problem. Okay, so we'll repeat. In this particular problem, both effective depth and also the area of steel we need to calculate. In the last problem, only area of steel was you need to calculate, because there they has given both the overall depth, okay, and the B, that is width of the beam. But in this problem, only the width has been given. You need to calculate effective depth and also the area of steel. Under these circumstances, what I am going to do here is, I am going to assume the section as balanced. Okay, once again, that is mu is equal to mu lim. Okay, that means we know the formula for mu lim. So that is mu lim is equal to 0.138 FCK BD square, which is equal to mu or 0.138 FCK. This formula holds good for Fe 415 steel, and mu is equal to mu lim for a balanced section. Next, calculate the effective depth. Okay, and next calculate the area of steel using this formula and area of steel. So like this, okay, we need to work out the problem. Okay, and we need to come across the problem. Okay, any doubt? Any doubt? Okay, let us work out one more problem. One more problem. Next problem is a singly reinforced beam. A singly reinforced beam, okay, is subjected to bending moment of 75 kilonewton meter. Full stop. At working loads. Full stop. Calculate the area of steel. Calculate the area of steel. Calculate the area of steel. Okay, use M20 and Fe415 steel. Provide, here one condition is given, provide effective depth is equal to 1.5 times the breadth of the beam. Okay, so like this they have been given. See, in the first problem B and D were given. In the second problem only B was given. In the third problem B is also not given, D is also not given. And we need to calculate the things. So how to proceed with this problem? Okay, once again, we don't know what is B. Okay, we don't know what is B. Let us consider it as B is equal to this thing. And they have been given effective depth is equal to 1.25 times the breadth. Okay, sorry, 1.5 times the breadth. 1.5 times the breadth. Next, FCK value is given 20. And then F5 value is given, that is 415 Newton per millimeter square. So, and then one more thing, he has given M value, okay, bending moment 75 kilonewton meter. Okay, you convert this into ultimate moment of resistance or ultimate bending moment or factored bending moment, that is 75 into 1.5. So this workouts to be 112.5 kilonewton meter or 112.5 into 10 to the power of 6 Newton millimeter. Is it clear? So next, so how to proceed with the problem? Okay, so now how to proceed with the problem? So first, let us calculate a size of a beam, because we don't know what is B and D. Without knowing B and D, you cannot find out the area of steel. So first, let us calculate the size of a beam. Okay. For this, okay, as I have stated, okay, assuming once again the section as balanced, that is mu is equal to mu lim. Okay, so you already know what is the mu value, that is 112.5 into 10 to the power of 6 Newton millimeter equal to 0.138 FCK BD square. Okay, so this is the formula for limiting bending moment or limiting ultimate moment of resistance for balanced section for Fe415 steel. Okay, so now let us rearrange or modify the substituted quantity. 0.13 into FCK is 20. Let us retain the B as B. They have been given that the effective depth will be treated as 1.5 times the B. That is 1.5 B square. Okay. So now substitute that. Okay. It will become B cube equal to 112.5 into 10 to the power of 6 divided by 0.138 into 20. Okay. Into 20. Okay. Into 1.5. Okay. So this workouts to be, okay, that is B workouts to be cube root of this workouts to be 262.63 millimeter. Okay, I cannot provide 262.63 practically. Let us round off to 265 or 270 millimeter. Since B is 270, I can say effective depth D is equal to 1.5 B. Therefore, 1.5 into 270. Okay. So, this workouts to be 405 millimeter. 405 millimeter. So, provide okay, 262.63 millimeter by 405 millimeter. Okay, so this is the effective depth you are going to calculate. So now once again, okay, how to calculate the area of tensile reinforcement? How to calculate the area of tensile reinforcement? So now I will teach you one more way how to calculate the area of steel for this. Okay, so now step number 2, area of steel. Okay, now to calculate the area of steel, I am going to use a formula, okay, that is XU by D. Okay, you know that for a balanced section, same thing, XU by D is equal to XU max by D. Okay, so let us substitute this. 0.87 into Fy into AST divided by 0.36 FCK into B into D, and XU max by D value for Fe415 steel is 0.48. Okay, now substitute all the parameters, okay, that is Fy, FCK, B and D. You will come across with a AST value of 1046.70 millimeter square. Okay, so this workouts to be 1046.70 millimeter square. This is the another way I have been calculated the AST. Okay, is it clear? Hope you have get clarified. In this particular problem, both B and D is not given, hence I have calculated B and D. And next, a very important thing, I have been calculated the area of steel using an alternative method. So the very important thing in the last two problems, that is in this problem, in the last problem, is whenever you need to find out effective depth or we need to find out the width, all those things, we are going to assume the section as balanced section, that is mu is equal to mu lim or XU is equal to XU max, and we need to calculate the B, D and AST. So this is the methodology we are going to follow. So with this I am going to conclude the session of singly reinforced beams. Okay, so these are all the analysis you come across in the limit state analysis of singly reinforced beams. Thank you.